Hi and welcome back to another video here in the Hidden Quantum Champion series. Today we are looking at again one of the big Chinese players in the field of quantum technology. The company is called CIQTEK and they are making quantum sensors and let's say measurement systems for science and industry. If you're interested in learning more about this specific company and also in general more about the, let's say, Chinese quantum technology ecosystem, make sure to subscribe to this channel because I'm trying to show you as many companies from basically all over the world in the space of quantum technology as possible. And with that, let's jump right into today's video as we are diving deep into CIQTEK. So here we are on their website. Up here it says CIQTEK. One thing that is important to note here, this website in this case is translated into many different languages. I think the company is operating across many different countries already globally, and that's not this time a website that I have to translate with my browser from Chinese into English. It's available in English already. Here we see already what are the typical products. So we see electron microscopes, TEM, and I think also SEM and FIB. I will talk about what those are and how those work later on. And then we also see this electron paramagnetic resonance spectroscopy. Maybe spectrometer device over here. So basically an NMR device. I will also talk a little bit about this later on. But there's also another product in their product portfolio that I think fits more the quantum sensing part. And that's of course also why I think they're relevant in the context of Hidden Quantum Champions. Besides, of course, creating these products, SEMs and TEMs that are relevant for basically everyone who's manufacturing solid state systems in the context of quantum. Now, here we see the different products again. Scanning electron microscope, that's what it looks like. I've seen many of those during my PhD times. So when we were producing the wafers with the nanostructures on there, and that is relevant for superconducting materials, it's relevant for nanowires, it's relevant for small quantum dot experiments. So if you're trying to confine, for example, charge and do spin qubits, if you have basically anything that is on a wafer or anything that is a nanomaterial, a scanning electron microscope is already very helpful. If you can add a focused ion beam, so a FIB, into that, then it's even better because with that you can even, let's say, cut inside your material and look from the side, like look at the cross-section of your materials and understand them even better. Then there's the nuclear magnetic resonance, NMR. So this is using magnets and magnetic fields and the resonance of molecules to these magnetic field changes or alternations to measure using a gradient of the magnetic field to measure or to create images of different materials. This is basically what you know from your MRI scanner if you have to go to the hospital and they put you into this tube and create 3D images of your body. There's also the electron paramagnetic resonance, goes into a similar direction, and then the gas absorption analyzer. So this is, I guess, for gas spectroscopy. If you want to, understand on a scientific level what kind of gases are in your environment, in your day-to-day air that you're breathing, you would probably use something that is similar to this. Here we see the different application fields. So you see science and technology, material science, chemicals, industrial, energy and power, and then biomedical. So this is something that is already being used in today's labs, in today's industry labs and academia labs. These are existing products, and here are a couple of metrics about the company. So this is 700 plus employees, 40% plus of employee dedicated to R&D, and then 480 patents pending or granted. So this is already a scaled up company. It's not, let's say, a startup with 2 or 3 people. But also the devices that they are creating, they are not completely novel. There are also competitors in the field. You can also buy, for example, a scanning electron microscope from Zeiss, just as one example, or transmission electron microscope from Zeiss. There are also other companies making NMR devices, So I don't know. You can find other competitors in those fields as well. Then here's the news section. I'm recording this in May of 2026. You see the news here from April. There's something, from April 2026. So, and also from May 2026. So this is very much up to date, as to be expected for such a company. We see here the FIB SEM, so scanning electron microscope and focused ion beam, prepares 5 nanometer chip samples for TEM analysis. Let me quickly explain what this headline is about. So just on the very, let's say, technological point of view, if we are looking at imaging itself, so if you're looking, for example, at your camera, then you can basically resolve certain things with your camera. So if you're zooming in at some point, you see that your image is getting blurry. And the same is true for microscopes. That of course has one thing to do with the number of pixels that you have on your detector, but actually there's also a, let's say, resolution constraint on the, let's say, smallest object that you can technically see. And there's this, there's also a name for that. I don't know what the English one is, but there's, let's say, a lower resolution range, and that has to do something with the wavelength. So if you're, for example, looking at infrared light, you have very long wavelengths. They can go up into the micrometer scale. So micrometer is 1 order of, like 3 orders of magnitude below millimeters. So still pretty large, but actually you cannot resolve, let's say, very, very small elements with that. And that's why you see that as the chips in our computers are scaling to smaller and smaller sizes, at some point also the light had to be scaled. So at some point it went from, I don't know, white light, or you could start with, let's say, completely mixed light. Then you would, let's say, pick specific light frequencies. You would go to blue, ultraviolet, and today there's like the extreme ultraviolet, because as you are, let's say, going into the more violet regime or even further up, the wavelength gets smaller and smaller, and therefore you can create smaller and smaller structures with those. Now, after the violet or the extreme ultraviolet, you will end up in the X-ray regime, and with that you can see even small, or could in theory see even smaller things. Now, the issue that you also have at the same time is the absorption properties of those materials. They also vary, and that's, for example, why X-ray is considered also a bit dangerous, right? You don't want to expose yourself too much to X-ray, because basically it gets absorbed by your body, by your skin, and it can have altering effects on the cells of your body, and that's why X-ray is considered dangerous. And usually infrared on the other side of the spectrum, right, on the longer range side of the spectrum, is not as dangerous. It penetrates through a lot of material without interaction. That's why it enables you to see certain things that otherwise you might not be able to see, like looking through packaging material. I talked about in a different video about how this can be useful also for industrial applications. Now, even with ultraviolet or extreme ultraviolet or maybe X-ray, at some point you reach a certain limit and you cannot go smaller, smaller and smaller. And that's where these electron microscopes become interesting, because electrons in the world of quantum theory, they are also waves, right? They are particles and waves at the same time. We talk about the particle-wave duality. So sometimes they behave like particles, but sometimes they also behave like waves. Technically, they always behave like waves, but sometimes you see it and other times you don't see it that much. Now, thinking about that, if you are sending an electron at a grid, like a multiple slit, like in the double slit experiment that you know from let's say, optics, it means that the electron can interfere with this multiple slits. And then if you're looking at the other side, for example, of those slits, you will see the interference pattern of these electrons. And that's more or less exactly what happens here. So the materials that we look at, they are crystals. So they are looking like these multiple slits in the experiment. And now you will see that if you are sending electrons on the surface, part of them will get reflected. And these reflected electrons, for example, they could be measured. You can also measure other properties, but this is just one example. You could, for example, also hit electrons on the surface and measure the light that is being reflected back when the electron interacts with the material. That is then in the X-ray spectrum, and then you could do an X-ray scan of the surface of your material, which might help you to figure something out about the materials that you are looking at, because the X-ray, let's say, fingerprint of materials is very different for different materials. So you could, for example, use that to scan what kind of atoms you have at the surface of your sample. But you can also, let's say, look at the backscattered electrons, and therefore you can calculate back what the surface of your sample looks like. And if you are doing that in a scanning kind of way, so that's the scanning part of the scanning electron microscope, right? If you have an electron beam and you scan it across the surface and you're always looking at what comes back, then you can basically create images from that, more or less. Now, you could also do the transmission one, right, that I was talking about before. So instead of looking at what comes back, you look at what goes through. And for that, you actually need to kind of cut very, very thin slabs of your material, because otherwise the electrons will never go through. They will just be stuck inside the material, get absorbed, right? And that's now where the focused ion beam comes in, this FIB. Basically what you're doing is you're using a specific material, can be very different, and you're generating ions. So you're ripping off one of the electrons from the shell. So you end up with an ion that's a positively charged atom that is lacking basically one electron in its shell. That's why it's positive charge. That's an ion. And this one you can accelerate with an electric field and bump it into the surface of your material. And then you basically hope that it rips off some of the material from the surface of your sample. And doing so, you can, for example, use this as a knife to cut things out. And if you combine that with this scanning electron microscope, you can now basically look exactly which part you want to cut. Then you turn on the FIB, you basically cut a trench, you cut another trench, and what you end up with is like a slab that is kind of, or lamella is usually called a lamella. You end up with this lamella, and this one you can then take for the transmission electron microscope to actually look at the crystalline structure of your material. And in a transmission electron micrograph, you can really see, let's say, the atom by atom kind of setup. You can see how clean your transition and heterostructures, for example, are. So heterostructures are, let's say, stacks of different materials on a wafer. Let's say you have a silicon wafer, you want to put silicon oxide and then silicon germanium on top, just as an example. You could look at this heterostructure in this transmission electron microscope, and you could see how clean those transitions are, if it's like really stacking well on top of each other, and also how the crystal lattice looks like, if there's like tension in the crystal, or if it's growing cleanly on top of each other. So you can do a lot of material research, which is very important for all of the quantum technology. That's, let's say, the zoom out on these microscope technologies. Now, the other thing that I found interesting looking at the products, and let's see if we can see that in here as well, is these ones here. So the scanning NV microscopes, and that's what I wanted to quickly also talk with you about in today's video. So NV for nitrogen vacancy, and I think we've talked about that before, but I actually wanted to go into this again. So these are nitrogen vacancies that are usually introduced into a crystal, for example, a diamond, and the nitrogen vacancy behaves like more or less an artificial atom, which is sitting inside the crystal that can, for example, be optically measured. So you could use a laser to actually measure its properties, and it's also very prone to magnetic fields. So you can use it as a magnetic field sensor. Now, if you, for example, put that on the tip of a scanning microscope, for example, an atomic force microscope, where you have a very, very tiny tip that can scan across the surface, and you can do that in a nanometer resolution. So you can really see, for example, if you have graphite, you can really measure the steps of the graphene layers that are stacked on top of each other. I've done that once in the lab. It's very fascinating. Now you could put this nitrogen vacancy in addition, and then you would also be able to measure the magnetic properties of this material in a very, very low resolved range, so in very small resolutions. Here it says CIQTEK, Scanning Nitrogen Vacancy Microscope, so SNVM, is an advanced scientific analytical instrument that combines optically detected magnetic resonance, ODMR, of diamond nitrogen vacancy centers with the scanning probe technique. This combination can be applied to the research of spintronics, multiferroics, 2D magnetic materials, superconductors, and so on. Superconductors are also very interesting. So this technology, this NV center technology, is working across a huge temperature range. So you can operate that at cryogenic temperatures, so inside a cryostat, which you need to actually create a superconductor, as well as at room temperature. So it's a quantum sensor that works in a very broad temperature range. And you can see that, and I think I didn't show that before, but actually if you would look it up, the range of products that they are offering is very broad. So I guess you can buy everything from the full system, probably including the cryostat, all the way to just the sensor. Here's the features listed again, right? So high quality NV diamond tip, quantitatively non-invasive magnetic imaging. Maybe also important to note the FIB that I was talking about before, right? The focused ion beam is actually ripping off materials. So the FIB is something that is invasive. It destroys the sample. You cannot put it back into original order afterwards again. Whereas here in this case, it's a non-invasive method. So it doesn't, let's say, destroy your sample. You can still use it afterwards. For example, if you're building, I don't know, a quantum dot for your experimental setup, you can do this as an intermediate probing mechanism, and then take the same sample again and keep processing it without having to throw it away. We see the ultra high spatial resolution. I was talking about that before. It's usually done using piezo motors. So they're using the piezoelectric effect. And with that, you can go down to, in this case, 10 to 30 nanometers of resolution. Ultra high sensitivity. So this is less than 2 microtesla per square root hertz. I think I've talked about magnetic resolutions in a previous video with another company that is active in the field of magnetic field measurements with quantum sensors. So check out the Hidden Quantum Champions playlist if you haven't seen that video. It's linked on the channel. And then supported ambient and low temperature, high vacuum conditions. That's also something that I mentioned before, right? So there's a broad temperature range at which this is working, and also high vacuum is a topic here. Here you see the different components, right? So there's the probe design, the optical design. Then I guess you can also see a couple of those images. This one here is very interesting. I think here you see probably this is the cantilever. And then here you see the diamond cube, which might be the tip. And inside the cube, you see those different NV centers down here, which are probably then being used for the measurement. You can also see this image here, where you see them fluorescing, the different dots, the different NV centers. So yeah, that's probably about the tip or the probe of this system. Here you see a couple of images from the applications. We talked about superconductors before, right? So there's a so-called type 1 and type 2 superconductor. In this type 2 superconductors, you can, usually these are the stronger ones, so the higher critical temperatures, they can absorb so-called flux quanta. So you see these magnetic fluxes that are penetrating the superconductor in specific areas. And these can also move in the surface, and they also reconfigure every time you warm up and cool down the system. And with these microscopes now you can actually measure them very nicely on the surface. And there's this ferromagnetic, antiferromagnetic, where you see the different domains forming in the material. So that's, for example, if you think about a nail, a rusty metal nail, usually it's not magnetic, right? But if you take a magnet and you rub it along the nail, then you can actually magnetize it, so it becomes magnetic. With that we actually mean we align the different magnetic domains, because in fact in the material, it's always ferromagnetic, just it doesn't have a net effect because these domains, these little areas within this nail, they're completely randomly oriented. And only when you do this move with the ferromagnet, with the strong magnet along those lines, you actually start aligning those different domains with each other. And that's why the overall system becomes magnetic or ferromagnetic. Now, if you, for example, heat it up above the so-called Curie temperature, so if you heat up the nail or if you hit it on the surface, then those domains, they start to lose their orientation, and that's why then it loses its magnetic properties again, or it's magnetization again, the magnetic properties remain. And then here you see the combination, right? So you have a CFM, an MFM, and an AFM. So that's basically the combination of what you can measure with this one device. And then you can combine all of these informations also into one, and learn about, let's say, the material properties better. Then, I mean, yeah, there's a lot about applications and I think also scientific publications that they are involved in, where people are also maybe tagging that they've been using instrumentation from CIQTEK across, let's say, the scientific domain. I guess that's also important for a scientific instrument manufacturer to show that people are actually using those. And then finally, there's this About tab, which I also like to usually close the video with. So let's quickly go through this as well. Global development and manufacture for high value scientific instruments. So CIQTEK's main business includes electron microscopy, so FIB, SEM, and TEM, nuclear magnetic resonance, NMR, spectroscopy, electron paramagnetic resonance, EPR and ESR, spectroscopy and BET, surface area, and pore analyzers. The company delivers advanced customized products and solutions across environmental science, biochemistry, semiconductor technology, and material science, empowering its customers to innovate and boost productivity. With a workforce of over 700 employees, 40% of whom are R&D specialists, CIQTEK operates 12 R&D centers, including the Engineering R&D Center, Ultra Clean Pilot Testing Center, Electron Microscopy Application Center, Optically Detected Magnetic Resonance Laboratory, and Precision Measurement Laboratory. Here, the main responsibilities, mission, vision, and values are mission, achieving the exploration goals of customers and create the future of humanity together. Vision is to become a global leader in the application of science and technology and in the science instrumentation industry. And then finally, the values: satisfy customer needs, sincere and realistic, open and innovative, aggressive and responsible, simple and sincere, united and cooperative. Again, the company in numbers, we've seen that already mentioned above, 190 plus PhD and masters. I guess here we see the whole company with this very iconic building that we've also seen before. 280 plus in the R&D team, 760 plus patents, software copyrights, intellectual property pending or granted, and 2,000 plus customers served, I guess, globally. Here you see the application fields, right? So high fidelity technology and innovation, and then here the new application fields. So masters the world's leading core technologies, in focus on high value scientific instrument as niche market, and then apply weak magnetic measurement to a wide range of industries, and that's what we've talked about in the last part of today's video. The company is based in China, in Hefei. We've talked about that one before, which I think is where also a lot of those quantum companies are based within China. And yeah, I think that's everything that I wanted to share with you today about CIQTEK. Again, the company comes from the field of scanning electron microscopes, focused ion beam scanning electron microscopes, and the transmission electron microscopes. They have also other big scientific instrument branches, including the magnetic measurement, and then also now the NV Center technology on top, which is, I think, interesting from a quantum sensing point of view. They are basically integrated in different stages or in different levels of the quantum technology stack. On the one side, they are a crucial instrument provider for the people that are creating quantum technology, including, for example, superconductor related stuff, right? So when you're looking at the superconducting single photon detectors, SNSPDs, I guess there it is interesting to use scientific instruments like the ones that are provided by CIQTEK, but then they are also using quantum technologies in their own day-to-day work, for example, when looking at those diamond probe scanning microscopes. And who knows, maybe one day they also include SNSPDs into their, I don't know, electron microscopes or something like that. Remains to be seen. I will definitely keep following what CIQTEK is doing. And with that, I want to close today's video. As always, make sure to stay hydrated, and I'm looking forward to see you in the next one. If you are subscribed to this channel, you will not miss out on it. Until then, bye bye.